All right, get ready for a deep dive, folks. A deep dive into a topic that's, well, definitely illuminating. We're talking the polarization of light.
Oh, yeah, this is going to be fun.
You sent us some fascinating bits from the Feynman Lectures on Physics, Chapter 33 to be exact, and it seems you're all ready to unlock some mysteries behind this fundamental phenomenon.
And I think you'll be surprised, how relevant this stuff is to our everyday lives. We're not just messing around with fancy physics experiments here. This polarization thing, it impacts everything. The sunglasses we wear,
Oh,
even how engineers make sure those bridges and buildings we use are safe.
all right, you've got me intrigued, but before we go too far, maybe we could start with the basics.
Sure, sure.
Feynman, he really emphasizes that light isn't just about how bright it is. It's this oscillating electric field, and get this, it has a specific direction of vibration.
Right, it's like a vector, not a scalar.
What does that even mean?
Okay, so imagine a ball on a string swinging back and forth.
Okay, I visualize that.
That's like a linearly polarized light. The electric field is vibrating along this single line. Now picture that ball swinging, but it's in an ellipse, or even going in a circle that's like your elliptical and circular polarization.
So it's not just like the electric field being there, it's how it's, wiggling and jiggling that makes it a certain type of polarization.
Exactly. And this isn't some abstract concept, stuck in textbooks. This is the light we see every single day, sunlight, lamplight, that glow from your phone screen.
Okay, yeah, we're bathed in it constantly. So is all that light, is it polarized in some specific way then?
Most of the light we see, it's unpolarized, actually.
It's unpolarized.
Yeah, meaning the direction of its electric field is changing super fast, like a swarm of fireflies, all blinking on and off randomly. Real chaotic.
Okay.
There's no consistent direction in how it vibrates.
I like that visual swarm of fireflies. But if most of this light starts out unpolarized, how do we get these different types you've been talking about?
That's the cool part. Let's use a simple example, something we see every day. Why is the sky blue?
Okay.
It's all because of this thing called scattering, and Feynman uses it as a way to explain how polarization works, in the real world.
So how does this scattering thing turn the whole sky into this big blue canvas?
Right.
What's polarization got to do with it?
Okay, picture sunlight, right? It hits the Earth's atmosphere, which is like a bunch of tiny air molecules. Yeah. When the light hits these molecules, it gets scattered in different directions. And here's the key. That scattered light, it's polarized now.
Okay.
Meaning its electric field is only vibrating in one direction. And blue wavelengths, they get scattered way more strongly than other colors, so bam, we see a blue sky.
Wait, so you're saying the sky is blue because of this invisible, polarization thing that's always happening up in the atmosphere?
Yeah, that's it.
Wow.
It's a really cool example of how this polarization we barely even think about, shapes how we see the world.
That's mind-blowing. So we've got scattering, right, causing the sky effect. What other ways does polarization show up in the real world?
There's another fascinating phenomenon. It's called birefringence.
Birefringence.
Yeah, it's a mouthful, I know, but stay with me. This is about how some materials, they have different refractive indexes,
Oh, okay.
depending on the polarization of the light passing through.
Refractive index. That rings a bell, like from high school physics, but could use a little refresher. It's basically how much light bends when it enters a material.
You got it. And with birefringence, that bending's different depending on how the light is polarized. Take cellophane, for example.
Okay, yeah.
It's made of these long, chain-like molecules. You know how it changes color when you rotate it under polarized light? That's birefringence in action.
Wait, you mean like those colorful plastic wraps they use for gift baskets and stuff?
Yeah.
You're telling me there's actual, physics happening behind why they look so cool?
Absolutely. And it's not just for looks. Engineers actually use this stuff in some really practical ways.
Like what? Tell me more.
They use birefringence to find stress points in materials, like in bridges or airplane wings.
Oh, wow.
The areas under more stress, they change how polarized light passes through them. You see, and that can reveal potential weaknesses, things you wouldn't be able to see just by looking.
So by basically looking at how light bends through something, engineers can prevent, catastrophic failures? That's incredible. I had no idea something as, seemingly simple as polarized light could have such huge implications. That's amazing. I'm, starting to see polarization everywhere now. You mentioned engineers using this. Are there, tools that use it?
Oh, yeah, you bet. And they're probably closer than you think. Remember those polarized sunglasses we were talking about?
Yeah, my fishing buddies, they swear by them. for reducing glare on the water. Seems like they're always reeling in the big ones while I'm stuck with a sunburn, in an empty cooler.
Well, there you go. Polarized sunglasses, they're a perfect example of polarization put to good use. It's those reflections, especially from horizontal surfaces like water or the road, they can partially polarize light.
Okay, right, right.
And those sunglasses, they're designed to block that horizontally polarized light, you see, which reduces the glare and lets you see more clearly.
So they're like little gatekeepers only letting in the good light. Maybe I do need a good pair. Help me see those fish hiding spots.
Huh. Might not guarantee a trophy fish, but yeah, they'll enhance your vision. But to really get how they work, gotta delve into Polaroid filters a bit.
Okay.
They're like specialized gatekeepers for light, not just for sunglasses, though. Photographers use them to make colors pop, cut down glare. Even LCD screens use them.
Okay, so they're called Polaroid filters, but are they like those old Polaroid cameras? I'm picturing like shaking a photo in the air, hoping it develops right.
That's a different kind of magic. Polaroid filters themselves, they're actually pretty simple. Imagine a fence, vertical slats, right? If you chuck a bunch of balls at it, only the ones hitting the slats head on get through.
Right, right, makes sense.
Polaroid filters, they're like that, but for light waves. The material only lets light vibrating in one specific direction through blocks all the other orientations.
So it's like a sieve, but for light waves.
Exactly.
That makes sense. What happens if you stack like two of them together?
Ah, now you're getting to the good stuff. If you arrange two, but their filtering directions are perpendicular, something really cool happens.
Let me guess. They block even more light. Double the filtering power.
You're on the right track. Filters crossed like that, almost no light gets through. Like putting a second fence up, but with horizontal slats this time, no matter how you throw the ball, it's getting blocked.
Yeah.
But here's where it gets wild. Feynman, he calls it the three Polaroid paradox.
A paradox. Okay, now you really have my attention.
So you've got the two crossed Polaroids, no light's getting through, right? But if you sneak in a third Polaroid between them, but tilt it at a 45-degree angle, suddenly some light gets through.
Wait, what? Seriously, it's like adding a third fence somehow makes it easier to get past the first two. How's that even possible?
That's the beauty of it. That middle filter, tilted just right, it acts like a go-between. Takes the light blocked by the first Polaroid, right, and shifts its polarization just a bit, rotates it just enough so that some can pass that final filter.
So it's not making more light, it's changing the light that's already there so it can sneak past.
Exactly. It's a perfect example of how even seemingly empty space, in this case between the filters, it can still mess with light when we're talking polarization. Light isn't just passively going through, it's being like manipulated, transformed.
Okay, my brain is officially doing backflips. We've got this invisible polarization making the sky blue, then this three-filter mindbender changing how we see light. What else is hidden in this invisible world? Okay, my brain is officially doing backflips. We've got this invisible polarization making the sky blue, then this three-filter mindbender changing how we see light. What else is hidden in this invisible world?
Well, get ready to have your mind really blown. Because remember, we've been talking about light, right? This wave-carrying energy.
Yeah, it's been illuminating, literally.
Okay, so get this light, especially the circularly polarized kind. It doesn't just carry energy, it also carries this tiny bit of angular momentum.
Hold on, are we saying light acts like a tiny spinning top, like as it travels through space?
You're actually closer than you think. Yeah, it sounds kind of crazy, but Feynman, he lays it out really clearly. Picture this. Circularly polarized light, its electric field is rotating, right? Like that corkscrew we talked about. That can actually make electrons in an atom start moving in a circle.
So it's like the light is, I don't know, transferring a little bit of its spin to the electron.
Exactly. There's this transfer of angular momentum from the light wave to the electron. Now, before you go picturing electrons doing pirouettes, the amount of angular momentum one photon of light carries is crazy small. But the fact that it exists at all, that's a pretty big deal.
Okay, I think I'm starting to get it. We've got this this hidden property of light, this angular momentum, and it's not just theoretical, it's actually doing stuff, affecting these tiny particles.
And it goes way beyond just the physics of it all. Scientists are looking at ways to use this angular momentum to manipulate tiny objects.
Oh, wow.
Think nanomachines with incredible precision. It'd be like having these super tiny light-powered wrenches.
Wow. We started with why is the sky blue, and now we're talking about building microscopic machines with the spin of light.
This deep dive has been quite the journey. And we've only scratched the surface. Polarization, it's everywhere, even if we don't realize it. 3D movies, the LCD screen you're probably watching this on right now, it all comes down to this.
So next time I put on sunglasses, look at the sky, even watch a movie, I should take a moment to appreciate this invisible dance of polarized light making it happen. Who knew light could be so complex?
Right. There's a whole universe of this stuff out there, hidden in plain sight. Feynman was right. Light is a fascinating subject.